Yes, same kind of guy. Previously, we talked about the KNORR synthesis of the 5-membered heterocyclics. Now let's talk about the KNORR synthesis and Hirsch-Widman synthesis. Here are the reactions. KNORR synthesis, KNORR created this reaction without the pearl. So from the ketones, this is a ketone, like any other ketone, and this is alpha amino ketone. This is the alpha carbon. We have amine. We have amino group here in presence of glacial acid. Acetic acid. It is glacial acetic acid. So it is the concentrated acetic acid which contains not more than 1% of water. It is very concentrated. So we get the pyrrole from ketone and alpha amino ketone. Then we have Hirsch-Widman reactions. This one is symmetrical and this is non-symmetrical. For symmetrical, we have 4 starting materials. This is ester, and this is a keto group. So this is alpha position from the ester. This is beta carbon. So it is beta keto ester. Beta keto ester. Also, this one is beta keto ester. They are the same. This one and this one. R2 is the same as R2 and R1 is the same as R1. So this one can be any group, can be ethyl group, propyl group, like any other group here, but it should be beta keto ester. Then this is aldehyde, and you have ammonia here. We can synthesize pyridine. This is dihydropyridine. Or you can call it, this is position 1 and this is position 4. 1,4 dihydropyridine. You see that this nitrogen is saturated and this carbon is saturated. But in presence of oxidizing agent, we can form pyridine, the unsaturated one. All the atoms are unsaturated in presence of oxidizing agent. We are going to see the mechanisms. Then we have this one, non-symmetrical. We have beta keto ester. No, this is now enone. This is enone. We are seeing enone, this one, oxygen and double bond here. This group is now attached to the beta keto ester, form enone. And this one, the amine, is already attached to the beta keto ester, also to form enamine. This is enamine. So for non-symmetrical, these two components, these two starting materials should be pre-formed. They should be prepared before, not like this one that they are all in the same container, then they react. They should be pre-formed independently. So why is it non-symmetrical? Here we are seeing that R2 and R1 are the same. R2 and R2, R1 and R1. So this side is the same as this side. If you put a mirror, this side is a mirror image of this side. But for this one, these R groups are very different. So this one is used to make non-symmetrical pyridine or dihydropyridine. So that this one is different from this one and this one is different from this one. So they are not mirror images. This side, in case it is formed, this side is not mirror image of this side. You are going to see the mechanism, but these ones should be preformed, not like this one. Then we have this reaction or formation of hydroxypyridine. This is hydroxypyridine. pyridine, or 1 for hydroxypyridine. This nitrogen is saturated and this carbon is saturated, but we have OH group. So this one, like for KNORR synthesis, we saw that we are getting the 5-membered heterocyclics from 1,4 diketone. But this one is position 1, this is position 5. This is 1, 2, 3, 4, 5. So it is 1, 5 diketone or dicarbonyl in presence of hydroxy, ammonia, and catalyzed by an acid. We are getting this product. Let's see the mechanisms. Let's begin with this one. We have a ketone and alpha amino ketone in presence of an acid. So our ketone, this one, this is R2, we have R1, and we have a ketone. We react with an acid. Remember, this oxygen is having lone pairs of electrons. So as it reacts with an acid, we shall form this product. With a hydrogen, but this one is now positively charged, it is unstable. So as it stabilizes, it creates a carbocation here. Then our alpha amino ketone, the amino group, will come. We have R4 and R3 with a ketone. To attack the carbocation. So we shall form this R1, R2, then we have N, hydrogen, and another hydrogen. R3 and R4. Then there is OH group here, but this nitrogen is unstable. It is positively charged. Then we shall have a proton shift. Proton shift shall remain with NH, then OH2, and it's a plus now. Hydrogen has shifted from nitrogen to OH group. R2, R1, and we have this. That's what we are having. As this nitrogen forms a bond here, as it forms a bond, this one breaks off. So we have R2, R1, N, H, but now plus, because it has used its own pairs of electrons. R3, then R4. We have this. So as it stabilizes, it pulls the lone pair back, creating a carbocation. Remember, we're having hydrogen and hydrogen. This carbon is still saturated. So as this one breaks, we are losing one of the hydrogen, forming this. We have formed a bond. Then we have R2, R1, R4. It still have hydrogen here. Then R3 and oxygen up. That's it. Then this oxygen has lone pairs of electrons, so can attack the acid. When it attacks the acid, we shall have this R1, R2, nitrogen, R3, then it is plus, oxygen is plus, it is unstable, then R4 and a hydrogen. This. Then, as it breaks off, it creates a carbocation. This bond will now come, uses its electron to attack this carbocation formed. Then nitrogen will form a bond here. So we come up with this NH, we have formed a bond there, R2, R1, and you have closed the ring, R4, R3, then we have OH. We have OH group, nitrogen's plus is plus. So that's what we are having. As nitrogen stabilizes, remember I have hydrogen there. This hydrogen will break off, so form a bond. Shall form this NH. We have formed a double bond, R1, R2, R4, R3, and OH. We have OH. So this is what we have. This oxygen still has lone pairs of electrons, so it can attack a proton. So when it attacks the proton, we shall form OH group. So you can just use directly this bond. So it attacks a proton. As it breaks off, we form a carbocation. This one, the bond changes to this position to stabilize the carbocation. Then nitrogen forms a bond. Nitrogen forms a bond. So we shall have this with a double bond. It's now positively charged. R2, R4, we have R1 and R3. We have formed a bond there also. This is what we have. Then nitrogen is unstable. It stabilizes by taking up the bond. This bond shifts to that position. Then here we have hydrogen atom. It breaks off to stabilize this carbocation. So it forms a bond there. We come up with this NH. Here we have R2, R4, R1, R3. A bond here. Then we have formed a bond here. This is the pyrrole. It is the pyrrole now. Pyrrole is formed. So that's the mechanism. That is the mechanism. At this step, you can first attack the hydrogen, then you form O with H2, point is plus. Then as this forms a bond, it breaks off, or you can just do it directly. Use the bond, attack the hydrogen. That's it. Now, let's talk about this one. For symmetrical reaction, the HANTZSCH synthesis. The mechanism, we have a beta keto ester. We have this. We have R2 here, then oxygen, and R1. That's it. Here we have hydrogen and hydrogen. Remember, as in aldol reaction, we saw in the very first video of synthesis, the base will come, which is now ammonia, takes up the hydrogen. As it takes up the hydrogen, this oxygen pulls electrons. Since it is electronegative, then this one forms a bond there. So oxygen pulls electron, creating a carbocation. This hydrogen is broken up. It's broken up by the base, creating a double bond. So shall form this. You have that. Then you have formed a bond here. That's what you are having. Then we bring our aldehyde. We have our aldehyde. As oxygen takes up the electrons, since it is more electronegative, creates a carbocation. That carbocation, as this one stabilizes, this bond attacks the carbocation. So we form this. You have R2, from this one here. Then we have this with O minus. Then this oxygen can take up hydrogen from water. From water, can attack the hydrogen. This one breaks off like that. So form this. This is R1. We have R with O minus OH now. OH. R2 and this. Still we have hydrogen atom there. We're having hydrogen atom here. A base comes again, takes up the hydrogen. This one pulls electrons. This one forms a bond there. Form this. This is R2. O minus. We have formed a bond here. Then we have R and OH. R and OH. That's what you're having. Again, this one can take up hydrogen. So shall have R1, R2, O minus. We have R up and OH2. It is plus and a double bond here. A double bond. So this one forms a bond back. Then this one forms a bond there. This one breaks off. That's what you're having. But these reactions, they are reversible. So there, we put double arrows. Then here we go. We have R1 oxygen, R2. This one forms back. R. So we are having enon. We are having enon. So I'm saying that we are using same principles for these reactions. So we have enon here. Then we have another keto, beta keto ester here. This one will also be activated like here. It will also be activated. So same step. Remember they are same ketones. So same step up to this part. So we shall have this. Now it is okay. R1, R2, or minus, and we have a double bond here. This is beta keto ester. This is now activated using ammonia. Same step to reach this point. So this one, as it takes electrons, it's electronegative, creates a carbocation. This one forms a bond, creating carbocation here. As this one forms a bond back, now this one will attack the carbocation. So we shall have R1, R, then here, R2 here, O minus. This one has closed the ring now. R2, R1. So this is what we are having. As this oxygen forms back the bond, and we have a double bond here. This bond was created. So this double bond attacks a proton from water. So from this R1 oxygen, R, then we have R2. Here we have keto group, don't forget here. So R2, oxygen and oxygen. So I think this is position 1, 2, 3, 4, 5. We have keto group at position 1 and 5. So same principles now here with those we saw in KNORR synthesis. We have our ammonia. Ammonia will come as it attacks the carbocation formed as this oxygen pulls electrons from this. You have R1, you have R, this, and R1. Then R2, oxygen. This oxygen is having a lot of electrons. Then form R2 and ammonia attached. It is now plus. It is plus. I see. It's like this. Then here we can have a proton shift. We have a proton shift. R1, oxygen, R, then R1 with this. Here we have R2. I think then R2 here and OH with NH2. One of the hydrogen has shifted to oxygen. Then this oxygen can attack proton. So it attacks the proton. We shall have this R1 we have R and R1 up. Then oxygen R2 here we have OH2 plus and NH2. So this one can be gotten from water. So this is what we have. As nitrogen forms a bond, this one breaks off. It breaks off. Space isn't enough, so let's rub here. So from here, we're having R1 and R1, then R2 with a oxygen, this one. Then you're having NH2, but it has formed a double bond. So it is plus. It is plus. Then R2. This is what you're having. Remember, we're having hydrogen there. We're having a hydrogen. So as this nitrogen pulls a bond back, this one breaks off, forming a double bond. So we have R1, oxygen up, and R1. Here we have R2 with oxygen. We have formed a double bond there, and NH2, then R2. So this is what we are having. Oxygen pulls electrons. As it pulls electrons, it creates a carbocation. Nitrogen attacks that carbocation. So we are closing the ring. We are closing the ring. So we shall have this compound here. R1, oxygen upwards, then R1 having N with two hydrogens, a double bond there, and R2 also R2. This oxygen can get a proton, so we shall have OH. You can just draw a bond like this to get a proton from water. So we're having OH, but this nitrogen is positively charged. It's positively charged. So we have a proton shift. This hydrogen goes to the OH group. So we form R1, another R1, you have R2 and OH2. It is now plus. Then NH, double bond, and R2. That's what you're having. So nitrogen forms a bond. When it creates a bond, this one breaks off. So having R1, oxygen, and R1. Here you're having NH and a double bond formed. Still have this bond, R2 and R2. Let's see. But N is positively charged. Here we have hydrogen. When it pulls electrons back, this one breaks off, creating a double bond there. So we're having this. Here you have formed a double bond, and you have this double bond with NH, R2 and R2. So we have this 1,4-dihydropyridine. But this one, in presence of oxidizing agent, if you put an oxidizing agent like manganese oxide, we have hydrogen atoms. This carbon is saturated. That's what we're having. So as oxidizing agent takes the hydrogen, we can form a bond here. When you form a bond here, this one will shift to this position, and nitrogen will lose this hydrogen. So we shall form R1, another R1. You have N. You have formed a bond here, also here and here. You have R2 and R2. This is the pyridine. This is pyridine. It has substituents. These R groups can be any substituent. This one can be ethyl group, also this one ethyl group. If this one is methyl, also this one is methyl. So both sides are the same. This side is a mirror image of this side. Okay, we had R group here. Please don't forget this R group here. It was present, so don't forget it. It is there. Meaning that here we had one hydrogen and R group. So we remain with R group. So R group can be a hydrogen, can be any other substance. So that's how pyridine is synthesized by symmetrical method of the HANTZSCH synthesis. Let's see now the non-symmetrical. Yes, MK the guy. For non-symmetrical, we have anion and enamine already formed. You have R1, here R2, double bond, R3, and another double bond. Then we have our enamine. R4 and R5 with NH2 and a double bond there. So that's what we are having. This nitrogen has lone pairs of electrons as this oxygen has. This oxygen is more electronegative to pull electrons towards itself. When it pulls electrons, creating a carbocation, this one forms a bond, also creates a carbocation. This nitrogen forms a bond as this one attacks the carbocation. So we have R1, then R3 upwards, R4, R2, this is O minus now, and the NH2 has formed a bond, so it is plus. R5. So that's what we are having. So I think as it tries to stabilize, here there is hydrogen atom, so forms a bond there, it is lost. As also this one tries to stabilize, forms a bond back. Here, remember here we formed a double bond. There's a double bond formed as this one attacked to attack a proton from water molecule. So we shall have R2, R4, then R3. We have lost this double bond. We have R2, then R5 and NH2 with oxygen atom there. So here we have a double bond. That's what we have. So as this oxygen pulls electrons back, this nitrogen has lone pairs, so it attacks the carbocation. So we form this R4. We have a keto group there, R3. Then nitrogen has crossed the ring. It has crossed the ring, but it has two hydrogen, so it is positively charged. Here we have R2 and R5. We have a double bond here. Then this oxygen, as we said, you can make O minus, then it attacks the hydrogen atom, or make O minus, then you have proton shift. Proton shift from NH. We have a double bond, then here we have OH, R2, R5, R4, R3 here. Here there is oxygen. Then R1. So this one can take up hydrogen from water. So we have this R1, R4, you have R3, so NH or H2 plus now, then R2, R5. As this nitrogen forms a bond, this one breaks off. So we form NH, it's now positively charged. Then we have R2, we have lost water, so you can say minus water. R5, this, and R4. R1, you have R3 up, and a double bond here. So that's it. Then here we have hydrogen, remember, as this pulls the bond, this hydrogen breaks off. NH, it's now stable, and we have formed a bond here. We have a bond here. We have R2 and R5, R4, R3, and R1. That's what we are having. And that is the one for dihydropyridine. In presence of oxidizing agent, you can form your pyridine. R3. So how is it formed? Here we have hydrogen, forms a bond, and this bond moves here. Then this one breaks off. So you have a bond here and here. Then you put your substituents. R1, R2, R5. So that's the pyridine. But this one mainly used for unsymmetrical synthesis. This R is different from this R. So when you put a mirror, this side is not a mirror image of this side, so it is unsymmetrical. That's how the mechanism is. Let's talk about pyridine synthesis from 1,5-dicarbonyl. For this last mechanism, we have this R1, we have R2. So it is acid catalyzed. So as in the pyridine, same principles we are using. We have a proton. This one attacks a proton. So we shall form R1, R2. This is with H, it's now positively charged. So as it stabilizes, creates a carbocation. Then this N, H2 with OH, comes and attack that carbocation. So shall form this R1. You have OH, R2, and N, OH, but it's now positively charged. So you have a proton shift. You have a proton shift. R1, oxygen, OH2, it's now positive, and N, H, OH with R2 here. This. As this breaks off, now nitrogen forms a bond. So R1, here we have R2 and N with a double bond and H with OH. It is plus now. Here we have hydrogen atoms. As it stabilizes, this one forms a bond. So we have R1 or R2, we have N, H, and OH. So this one attacks a proton. So it attacks a proton, shall form this R1 or H. It's now plus with R2, N, H, OH. So as it stabilizes, creates a carbocation, this N attacks. Remember, we have a double bond here. We have a double bond which was formed there. So we form this R, N has closed the ring. It has hydrogen and OH, so it is plus. A double bond here, R2. Then here we have OH. Then we have proton shift. N, OH, R2, double bond. Here we have OH2, it's now plus, and R1. So nitrogen forms a bond. This one breaks off. You have N, OH, but it's now plus. R2, you have R1, you have lost water. You have lost water. So as this one stabilizes, remember you have a double bond here. Here we have hydrogen and hydrogen. So one of the hydrogen forms a bond there. So we shall have this N, OH, R2, R1, double bonds. So we're having this. So if you add oxidizing agent, here we have hydrogen and hydrogen. So it takes up one of the hydrogen, forms a bond there. This one forms a bond there, OH group goes off. So we form N. We have formed a double bond there. This one shifted to this position. We have here OH group was lost. So R2 and R1. So this is how we form pyridine from 1,5-dicarbonyl. These R groups can be any substituents. If it is just hydrogen, so it becomes pyridine, which is unsubstituted. If they are substituted, it remains pyridine with substituents. So that's how the mechanism is. Let's have some examples, some trial examples, such that you can try out. Some kind of guy. If you can do all these questions, mean that you can do any question regarding whatever you have discussed in all the videos about synthesis of heterocyclics. Just do these questions, try them out. Please don't forget to hit that like button, share the videos, and if you haven't subscribed, please subscribe. Yes, same kind of guy.